Hello and welcome to today's e-learning class. Elements of Turbulence Modeling is our course. The number is EL139 and this is our final session 2. Our tutor, Cameron Bellotti, is here and ready to get started. So Cameron, if you're ready, I'll go ahead and turn the class over to you and let's just get going.
Okay, great. Thank you. So this is, hopefully you're now looking at the title page. This is our session 2, as Margot mentioned. And we're going to get started. We were a little delayed trying to get people, coming in. Apparently we have some live, our live audiences or participants are slow to get in. So on our session 2, session 1, what we discussed was really the challenges that turbulence flow poses to us. Mainly, it's at the small scale. In order for us to resolve them, we require us to have very fine grid in order to pick up all the scales, and also the fact that turbulence is not really in a steady flow. So even if you go with direct numerical simulation, you still have to run many cases, and at the end, average some of those things because you don't have you have non-linearities in a way, and very unsteadiness. So this part, we're going to talk about the solution that we've been using, the technique that we've been using for a number of years now, for a few decades now, in order to get the effects of turbulence. So if you recall from session 1, what we said when we go ahead and I guess if you remember, we said if you look at the velocity component or temperature or pressure, you could put any of those parameters into two components. One is time averaged, for example, and then the next one would be the fluctuation at any instance from that average. Which we called, if you remember, we called them like U bar, V bar, and so forth, or T bar. Those are the fluctuations. And after we went through the averaging, unfortunately, our equation looked the same except for additional terms that they were there. And these additional terms are additional unknown, so to speak, and we need to somehow be able to model these things because we don't really have good equations to do these. So what we want to do is come up with some sort of technique to get the general effect of turbulence without spending extreme amount of time and resources to get that. So now we're going to talk about turbulence modeling. So in terms of coming up with these equations for these type of terms which are present in our equation, there are several ways to do this thing. The one that's mostly used, the most popular one, I guess I should say, is based on Business hypothesis. So what it says is trying to create a relationship between these Reynolds stresses, these terms that we're talking about, and the velocity gradient. So somehow if you go back to this equation, somehow if you could create these equations that looks like these terms in the equation, that looks like these terms in the equation, so these are the velocity gradients, then we probably have something here. So if you look at these things, as I mentioned, these are called Reynolds stresses because in dimension-wise, they very much look like the dimensions of our shear stress terms. So somehow we need to go, and the hypothesis is, therefore, maybe we could write them in that looks like something like this. How we do this is based on dimensional analysis. I just mentioned, they have the same dimensions and so forth. And one of the assumption is that this new term that we're going to pick, and I'm going to explain that again soon. For example, mu t or nu t, which is either eddy viscosity or turbulent viscosities, they tend to, what this assumption says, this hypothesis, that these are isotropic. That means that they're scalar values. There's no direction to these things. So that's one assumption that I think it does hurt us at some point, and I'll explain that again. The other thing is another assumption or another model is based on Reynolds stress transfer model. What it says is instead of trying to relate these into these parameters, why don't we have an equation for these terms, for these terms individually? So let's have additional equations and have them somehow calculated. Again, it requires some modeling, but the good thing about it is this assumption that we said these are scalar and they have no direction, that assumption is no longer there. So in that sense, it's nicer. But at the same time, as I said, maybe we have about 6 of these Reynolds stresses, so we have to have additional 6 equations, for example, that we need to work with. So that makes it a little bit more complicated. It has something about the scales of these fluctuations. They're much smaller than maybe average value, and in terms of scales, so that becomes a little complicated in terms of numerics, and then they're expensive to solve because, like I said, we'll have many more equations to solve for. Another one is again going through this type of assumption, but instead of having some sort of linear model, we would have a nonlinear one. So that's a little improvement in some ways over Buzanek's hypothesis. So let's see what that Buzanek's hypothesis is talking about. As I mentioned, we're looking to transfer these Reynolds stresses, the terms that look something like this, into velocity gradient, something like this. So we say the Reynolds stress is related to this velocity gradient with the help of this mu t, which is we call turbulence viscosity or eddy viscosity. So now we've got a relationship between Reynolds stress and velocity gradient with mu t in there. So if you look at that, and then the other part is we're going to say that for the temperature terms, we need something called turbulence conductivity, and we have to have an equation for that as well. So now let's take a look at what our equation is going to look like. If we make this assumption, then this is again two-dimensional incompressible equation with constant properties. So it's a simplified form of one of the equations. But if you look at it, so our continuity equation looks exactly the same. Our momentum equation looks very similar to that, except mu t has mu and plus mu t. I mean, mu has mu and plus mu t. So this is where we added this additional term because of that Reynolds stress term. So this is the additional unknown that we added. But now our equation is a lot more simpler than these equations. So instead of nu, for example, we'll have nu plus nu t. Okay, so that's what it looks like. So and then we'll kind of drop this one. Right? So having said that, now you look at it and you say, okay, that looks a lot nicer. Unfortunately, in our equation, we still have mu t and kt. They're still unknowns. So we're still facing a closure problem. We need two more equations for these things. So that's where turbulence modeling comes from. Coming up with equations for mu and mu t and kt. Kt is sort of easier because it's related to mu t through Prandtl number, turbulence Prandtl number. So we've got to come up with something for this mu t. That's where turbulence modeling is. Unfortunately, there are a number of different turbulence models that come up, have been proposed and been used. None of them are good for all kind of flows and all kind of flow regimes. Each one has their own effectiveness for different type of flows. And they kept, and we often have updated them, and there's many different versions of any of these models out there. So that's why it tends to add more to the confusion of what we need to use and how we need to use it. So that's why we have a course like this to talk about these turbulence modeling, because there is not one that is acceptable. There's many different kinds. So one example, for example. One example of turbulence modeling, random turbulence modeling, is our well-known K and epsilon model. So, for example, this mu t can be represented into K and epsilon. K is our turbulence kinetic energy. And the epsilon is the rate that the turbulent kinetic energy is dissipating. So if you replace mu t by K and epsilon, now you have two unknowns to deal with. So if you, for example, come up with an equation for K and an equation for epsilon, now you'll again try to fix that closure problem. So this, depending on what kind of equation we use for K and epsilon, then the degree of complexity comes into picture here. So we'll talk about that. So, but that's one example of turbulence modeling. How do we come up with an equation for mu t? Well, we'll replace it with K and epsilon. Then we'll have an equation for K, one equation for epsilon, or some kind of relationship for epsilon. So along those lines, we'll be able to get the effect of turbulence. One of the issues we deal with in turbulence flows is, of course, as I mentioned, one of the biggest problem we have at the early part I mentioned is the wall-bounded flows. That one of the major categories of turbulence is wall-bounded flows, turbulent flows. So, and that having walls in our domain, which happens quite often. I think majority of cases we deal with is there is a presence of some sort of wall configuration in the flow. So we need to deal with walls, and walls make things very complicated. And I'll talk about it. And the reason I'm going to talk about it is because when we do something like K epsilon model, we need to deal with walls, and having the presence of walls makes things difficult for us. So let's talk about dealing with walls to begin with, and why those challenges come about, and how do we go about responding to those challenges. So walls generate vorticities and turbulence. small vortices are rolled up and ejected from the walls. They are, and then at the smallest scale eddies, they get dissipated. So walls impact our energy cascade. Small vortices create big ones, and then they tend to dissipate the turbulence kinetic energy at the smallest scale. And walls do affect our turbulence length scale because they do create vorticities that are constrained, and because of the presence of wall in one direction, maybe gives it an orientation of some sort. And I talked about this a little before, and I said, that's the business hypothesis. Unfortunately, assumes there is no direction to eddy viscosity. So anyway, so having the wall causes large gradients, and that kind of exhibits the turbulence length scale exhibits complex behavior. But it is important for us to accurately model the wall. Why? Because it would affect how we calculate frictional drag, pressure drop, thermal performances for heat exchangers, and so forth. So there are major effects because of the presence of the wall. Therefore, we need to deal with walls. We need to accurately model them. And remember, we talked about we need finer meshes where we have gradients. So we need better meshes as we get closer to the surface. So and if we put way too much mesh, that means it becomes very, very expensive. We can't really just add points indiscriminately. So let's take a look at what happens near the wall. If you look at the pictures near the wall, so if your wall is sitting somewhere in here, in this area, zero velocity, and eventually reaching boundary layer thickness, edge of the boundary layer thickness, where we reach the free stream velocity. So along the way, we're gonna see small scale eddies near the wall, and the larger scale eddies a little bit further away from the wall. And if you look at it, you could divide this thing to several layers. The one near the surface is called inner layers, and then the flow is fully turbulent, and I'll talk about this a little bit more. It's called outer layer, and then the overlapping region is called the log layer. So one thing is that we consider is the law of walls. So the law of walls says average velocity of turbulence flow at a point is proportional to logarithmic distance of that point to the wall. So that's where the log layer kind of comes into picture. In this point on, we say, so imagine at this point on, we say the average velocity at these points is proportionally to the logarithmic distance away from the wall. So having a distance away from the wall, so we need to know what distance away from the wall we have at any point, because that's going to determine if the law of walls is valid or not. And I'll tell you why when we'll talk about this. So in the inner layer, this is where the viscous forces are very dominant. And we call that viscous sublayer and buffer zone. So really, this is where viscosity effects are very, very dominant and tend to be, we call them like laminar sublayers. So this is where things dissipate. In outer layer, you tend to get these large eddy dissipations, and that's really dependent on what the mean flow is coming in. And that's the log layer, as I mentioned, this part, it's where we say, okay, the law of walls applies. So let's introduce y plus. Remember I told you we need to know the distance away from the wall. This is what we're looking for. So one way to do it is calculate this distance away from the wall and call this one a y plus. If you non-dimensionalize it and you call it y plus. And let's describe what that y plus is. So here's your wall, and the flow, and this is away from the wall. So if you look at it here, y is this direction. This is the wall at the bottom here, and in this figure, wall is here, and y is in this direction. So as I mentioned, near the wall is viscous sublayer, and then there is a buffer zone. So this makes up the inner region, and then you have the outer region at this point, and between you have the log layer, which is the log wall valley. Now, if you look at the velocity at any point, away from the wall, there is a parameter we call non-dimensional velocity, u plus. U plus is u over u sub tau. What's u sub tau? That's the friction velocity. It's tau wall divided by density to the power of half. So that's one non-dimensionalized in the u plus. Y plus also is non-dimensionalized. Y is also non-dimensionalized using u tau and nu. The dynamic viscosity. So y plus is this distance away from the wall, non-dimensionalized like this. Remember, let me emphasize again, in the viscous sublayer, we have mostly dissipation. Dissipation is much greater than production. In log layer, in the overlap region, production is equal to dissipation. So whatever we produce is equal to this, whatever we dissipate. And in this part, of course, we produce more than we dissipate on the outer region. So we know what this y plus is now. Now we've got to come up with ways, now that I described this y plus and u plus, we're going to go back a little bit later on when we talk about two equation models, and I'll describe this a little bit more in further. So the turbulence are categorized, remember this what I said here. I said I got to come up with an equation, we have to come up with an equation for mu t. So one is maybe have two additional partial differential equations, one for k, one for epsilon. So two additional PDE needed in this case. And because we need two additional PDE, one here and one for epsilon, we call this a two equation model. So if you only use one PDE to describe this mu t, then it's called the one equation model. Two equation model, I just talked about that. Maybe you have three equations. So these are all maybe three PDEs. So that's what it means. Two equation models are two PDEs and one PDE and so forth. If you use just sort of a algebraic model, no partial differential equation, that's called zero equation or algebraic model. And then we keep going up until we get to LES and DNS, and in between there are some hybrid methods, and we're going to talk about those a little bit. So as we go this direction, we're introducing usually, not always, more physics at the same time more computational time as we go in this direction. So let's look at the one equation model. We say mu t, this should be mu t, is equal to rho. This is the kinetic energy to the power of 1 over 2 times some sort of length scale here, algebraic equation for length scale. So if we have a PDE for K, and then have some sort of relationship for some sort of algebraic relationship for this L mu or L epsilon, then we have a one equation model here, a single transport equation. And often in the past, the way we came up with the value for these length scales was just the distance of wherever we are away from the wall. But you can see that becomes a little difficult because if you have a complicated configuration, the distance away from the wall is sometimes it's not easy to specify. So this one equation model had its shortcoming, because you could have a one equation model for K, but the L was kind of having a hard time doing that. So people came up with two equation models, and they said one equation for K and one equation for epsilon. But before I go to a two equation model, let me give you one more of these one equation models. And this is a little different from the one I just showed you. This is different from this one equation model. This one is called the Spallard-Almaraz or SA model. It's one of the more popular models, and it only uses one PDE. Okay, which is a good thing because it's very economical in a sense, and it's easy to implement. And what they did was instead of replacing this mu t in terms of K and epsilon, we'll replace it with this term, and then have an equation for directly put an equation directly for that one. So the mu bar, the nu bar. So this is the partial differential equation for nu bar. So one equation model is used, and again it has three terms in it. It has the generation of the turbulence, diffusion of the turbulence, and destruction of turbulence in a dissipation wise. So now you have one equation, and it gets away from K, so which is nice, and it doesn't need that length scale that we were talking about, the L mu or so. So in this case, because of you didn't have to specify that, really got popularized when you were using unstructured grid, because having the distance away from the wall was not easy to calculate all the time. So this kind of took off, and it's been pretty powerful for aerospace application. It's very easy, economical to implement. If you're writing the code, it's easy to write. It's pretty because it's one equation model. It's very economical. It very works well for wall-bounded flow, turbo machineries. If you have adverse pressure gradient, if you have mild separation and recirculation, again, it does very well. If you have massively separated flows, so imagine you have flows over airfoil and you got massive separation happening here. That doesn't do so well in those kind of applications. Or if you have shear layer or decaying turbulence. So these are the places where it does fail. Or it doesn't do so well. Maybe not fail, but it doesn't do so well. So this is an SA model. So let's talk about two equation models, because that seems to be the one mostly used and it's the workhorse right now. One equation model requires the turbulence length scale. Remember, that's what I said, that the L mu, this again, the L mu, we needed to specify. So if we have complex configuration geometry, it's kind of difficult to set that up. The two equation model says, okay, why don't I create one equation for K and one equation for epsilon. One is for K, one for epsilon. Sometimes this epsilon is replaced by omega, which is inverse time turbulence time scale. So I'll talk about that a little bit later on. That's basically epsilon over k. That's your omega. So there's many different kinds of these, and it was built in order to not to deal with length scale. But it poses its own problem. So K is often used for specifying the velocity scale, and epsilon is used to specify your length scale. Okay, so remember, we're doing this modeling at because of the problem we have at the smallest scale. So large scale, yeah, we need to model, but the small scale was the one causing us problem. And here we specify mu t in terms of k, but k uses the mean flow information for us. So even though it's giving us the velocity scale, but we're really relying on the mean flow to give us, on the large scale eddies to give us that information, this is what will eventually cause us some trouble. Okay, so K is taken from the large energy containing eddies, and we were looking for scales at the smallest scale eddies. That's so you could see the problem here. Epsilon also is causing us problem. Epsilon is going to give us the dissipation rate of the smallest eddies, but again, it is based on this assumption that the smallest scale eddies are going to be coming from the same large scale eddies. So let me read here. It is assumed that energy of the large eddies eventually cascades down to small eddies. This is based on this Kolmogorov assumption, equilibrium assumption, that we could say epsilon, because we don't know what the epsilon length scales are, right? So we don't know what the small scale length scales are. Based on that, we say, okay, these dissipation rate that happens, so whatever we get at the large scale is breaking down to smaller and smaller and smaller. So whenever we get this dissipation rate, we could use that at the smaller scale eddies. That's what this one is saying. So using that assumption, now we got two parameters to deal with. One is K and epsilon. This should give us the velocity scales and length scale that we needed. So we'll come up with an equation for K and one partial differential equation for K and one partial differential equation for epsilon. And each one of them will have the convection term, generation term, diffusion term, and destructive term associated with them. One thing you need to pay attention to, that in these equations, you'll come up with these parameters. They're everywhere. Like 5 of these parameters are in the equation. Okay, so even though we created 2 partial differential equations, now we've got 5 other unknowns in there as well. So how do we deal with these 5 unknowns? Instead of having 5 additional equations, people said, okay, maybe we will look at it and kind of determine them, set them as constant, and determine them from experiment. So they come up with some sort of generalized flows, like flow over a step, flow over a flat plate, and those kind of stuff. And they came up with these values for these. So these values are called these constants, if you use those values that came from these generalized flows, those are called the standardized Navier-Stokes equation. So if you look at the, let's say in ANSYS Fluent, you want to run K epsilon, these are set default as these values. And if you use that, you're using the standard K epsilon. If you want to change it, I mean, you have an option, but you need to know what to change it to. So we'll talk about that a little bit. So constants, these constants we talked about have been determined and calibrated using simple flows, as I mentioned, flow over a flat plate, step, those kind of stuff. And we compare them against experimental results. So the standard K epsilon refers to these values being K epsilon model, the standard K epsilon model, is really economical. That's why it's used so much. And then one of the things is it's really simple to implement. So that's why it's written in the code often. One of the good things about it is it really gives you, it doesn't hurt your convergence. It's very robust in that sense. For many different types of application, it does well. And it does give you accuracy for a wide range of flows, not for all kinds. So where we have problem is where we have, for example, a strong swirling and rotating flows, or separated flows with flow curvature. And you can see this, the stream curvature occurs due to the separation. So maybe near the wall, if you have sort of velocity being, gradient being only in one direction, but as the streamline has curvature, so flow over curved or stream, where if you have separations, then you need to deal with other components as well. And it's not only one component that you have to deal with. You have to deal with those two components. So I have written it in red in here, and I'll read it with you, and we'll discuss that. So we said, due to business assumption, a linear relationship between turbulence Reynolds stress and mean shear strength. So we said, remember we talked about this thing. We said there's a really linear relationship between Reynolds stresses and the mean shear stress. K epsilon does not capture the extreme sensitivity of turbulence to secondary shear strain. So because of this, this assumption works well when you don't have massive separations, but when you have or very separated flows. But when you do have it, then things start to fall apart a little bit. It doesn't do well for non-circular ducts or axisymmetric jets. So there are problems with the standard K epsilon model. And then there's other problem. Having the wall. We remember I had a couple of slides about dealing with the wall. So K epsilon, when near the wall, has to be modified, adjusted, or do something about it when it gets near the wall because of that assumption. I'll talk about that. Basically, let me read it here. K epsilon is fully turbulent region. So really, K epsilon, because of the law of walls that we talked about, right? It's based on the fact that the velocity it's proportional to the distance away from the wall, and this is true maybe in this region, not true in this region, where you have a viscous sublayer and buffer layer. So what do we do? If if K epsilon works here, but not here so well. And if you could look at it here, this is going to be your viscous sublayer. This is the buffer layer, and then you have the inner layer and outer layer. Okay. So in this area, we have a problem. And then the other part is the K epsilon assumes that eddy viscosity, we talked about this, right? Eddy viscosity is isotropic, so there is no direction to eddy viscosity in this region. And we know that there is, because there is a wall in here, and the vorticities gets orientation here. So, and we know these flows are not isotropic near the wall. So in order for us to use K epsilon near the wall, we have to do something special. So what do we need to do? There's two options for us. One is using some sort of function at this point, and then don't model this part, and just use the effects and put it right here, and then we'll go up in that direction. That's one way. The other way is use K epsilon all the way to the wall, and then use some sort of corrections or something like damping to get it to work in this area. But in order for us to know where we are, in order to do this kind of things, we need to calculate the y plus. Remember, y plus was the distance away from the wall, and it's a non-dimensional number. So what we say y plus of a grid, in your grid, what it really means is the very first point in your grid. So if your grid is something like this, the very first point away from the wall, the distance of that from the wall is y plus. It's the non-dimensional distance from the wall. It's the very first point. So let's take a look at this thing. So I said there's two approaches. One is near wall model, where we could use the K epsilon and we go all the way to the wall, even to the buffer layer and sublayer. And what we need to do is do something different. So very first grid point near the wall, in order for this to work, we need to create a fine mesh so we could resolve this, so we can model the grid, model it all the way to the wall. So the near wall model asks us to go all the way to the wall, and because K epsilon will have problem, we'll introduce some damping function into it. And where do we get this damping function? We either use the experimental or direct numerical simulation or something to create that. But what requires is it's a very fine grid all the way to the wall. So very first point away from the wall should have a y plus of close to 1. Remember, this is a non-dimensional number. So this requires a very fine grid, but it models it all the way to the wall. The other option would be wall function. We'll say, all right, so since K epsilon is not valid in this region, we'll start from where it is valid on. Okay, so what do we do in which for this layer? We'll put a function in here and get the effect. So sort of use it as a boundary condition. Get the effects of it through this function and put it from this point on and use it as a boundary condition. So here we'll create. Here we would look at it with turbulence modeling. Here we just use that function. So in this case, the flow near the wall is not resolved, but a semi-empirical function called wall function is used for this region. So what the function does is connect my wall to my region that I'm interested in. Connects the wall conditions to the dependent variable near the wall. So what happens here is, now that we're going to use wall function, we really don't want to have a grid that falls in this region. Okay, so you want it to be right at the edge of this region where we could put that wall function.